to arbitrary number is well defined. So y is a function of x for all real numbers x. But here, if we use this notation only defined for rational numbers. So rational number stands in real number line. And if we consider if x is a rational number, this one and this one the same. For example, if a equals 2, 1, and here's a square root of 2. Here, this number is defined. But undefined, because this is an irrational number, square root of 2, irrational, right? But again, this function is differentiable function. It's a continuous function. So since here, nearby this position, there are so many rational numbers. So the behavior of this function can be determined completely by real numbers nearby here. This is exact the notion of limit. We can define this one to be this one. So here we make a definition. If a is a positive number, we define a raised to the x power is defined to be e x times ln of a. Whenever a is a positive number and x is a real number. So here, we're defined. Here, for rational number is defined, but irrational number, for here, undefined. We can define a to the x in terms of the natural exponential function and the natural logarithmic function. It's very perfect. Perfect. So gradually we extend the base e to arbitrary positive number a. So we call such a function a general exponential function. And e to the x is the natural exponential function with base a, not e, with base a. Okay. Let's study the consistent. If a equals e, no problem. So you will see two, because this is 3 is it's an integer. Of course, it is a rational number. On the other hand, this one equals e 3 ln 2. Same. because we put into this one. Okay. So we learn the exponential function in terms of the natural logarithmic function and the natural exponential function in a natural way. Not begin with a counting of 10 fingers. Again, okay, laws of exponents. For the first one, x, y can be any real numbers, not necessarily integers. A raised to x plus y. What is this? By definition, we define this in terms of the natural exponential function and the natural logarithmic function. Use the properties of real numbers, the distributive law. Then use the laws of exponents for the base e. Again, by this definition, this is exactly a to the x times a to the y. A. Ex ln a, y ln a. Yes, distributive law. Here, x ln a. Oh, yeah, it's a mistake here. Thanks. Merci. Gracias. Evcharisto. Спасибо. Good. For B, again, this is exponential y of Ln of ax. Then exponential for y, Ln of ax means e x ln a. definition. Here. A to the x to the x equals e to the x times ln of a. Okay, cancelled. Use the associated law of the operation, multiplication. Very good. Of course, once A is true, then x minus y equals ax over ay. Whenever a is positive, x and y can be arbitrary real numbers. As before, here we already used the property A, this one. Next, we will learn the calculus for general exponential functions. Yes, compare this with this formula. So, the derivative e to the x equals e to the x itself. But here, the derivative a to the x equals itself times ln of a. Of course, when a equals the particular number e, ln of e is 1. So, consistent. Okay. They are consistent. Consistent. Once we have this formula, then we have so here, if a equals 1, then the numerator will be 0. Okay, let's prove a and then b follows from a. Again, what is a to the x? By definition, the only thing you can use is definition E x ln a. So if the exponent here is not x but a u, EU, this is a u. Times du dx. Here we are differentiating this one with respect to x, So a here is a constant, The first factor is a to the x, and the second one is ln of a. B follows from A. We can differentiate this one